I try not to send me emails at like 1:30 a.m. because there are times where I woke up, checked the email, and I felt compelled to answer the question. Okay, yeah, let's move on to the next tutorial. So that this tutorial will be surrounding unsteady flows, clearly. Okay, and there are 5 questions to this tutorial. Okay, like I said, okay, some of these I mean, these tutorial questions, they're not difficult, but they could be challenging to some because this is the first time that you guys are encountering unsteady flow questions. So don't worry about this. Let me quickly run through the solutions and you guys hopefully will have a much better idea. Okay, so take a look at question 1. We have a ship log. What's a ship log? It's like a ship dry dock, so as to speak. All right, so basically a log is whereby a ship, all right, basically gets towed into the log, and then they drain out all the water so that people can repair the ship, right? The ship's hull especially. Okay, so let's say we have a ship log. Yeah, it's got 2 vertical sides. Okay, and water enters or leaves this ship log through a conduit. Conduit basically a pipe. Okay, all right, through a conduit area of cross-sectional area A. Okay, sometimes conduit may not be a pipe. It's just an opening in the wall. Let's say, all right, it's a concrete a viaduct, so as to speak, right? Or basically a hole that's pre-built into the concrete walls and so on and so forth. Okay, now the flow through this conduit is given by this formula. All right, Q equals to CD. CD is not drag coefficient, mind you. All right, CD will be the discharge coefficient. Okay, Q equals to CD times A. A will be the cross-sectional area of the conduit. All right, into 2GZ square root. Okay, now where Z is the variable difference in the level between the water surface in the log and that outside. Okay, so usually what happens is a ship log. Okay, when you pump out the water, it enters into sort of like a reservoir. And then when you need the water again, all right, you pump the water from the reservoir back to the ship log. Okay, so based on this information, we're asked to do a few things. A, show that the time required for the water level in the ship log to drop from a certain height Z1 to another height Z2, all right, to drop is, all right, this expression over here. Okay, so that's for part A. For part B, assume that the ship log measures 100 meters in length, okay, 30 meters in width, and the discharge coefficient, the numerical value, is actually 0.5, okay? Now, if the water surface in the log is initially 12 meters below the level of the surface of the upstream water, how large must the conduit be if the log is to be filled in 10 minutes? In this case, we're talking about filling. Part A talks about water leaving the ship log. Part B talks about water entering the ship log. So there are some subtle differences that you guys will have to watch out for. Okay. Now, let's start off with the formula. Or should I say, let's start off by listing out the formulas we're given. In this case, Q equals to CD times A into the square root of 2GZ. Okay. And I always find it very useful. I'm quite sure I've been pounding on this for like 2 million times already. But all right, I think it always helps us engineers just to provide a very, very simple sketch. So we know that this ship log basically has got 2 vertical sides. So it's sort of like a rectangle, isn't it? Okay. So let's say the ship log's the water level, let's say, all right, is here, and the difference in the height between the water level in the ship log, all right, and that at the drainage point is Z. Okay. And surely, if we're talking about, you know, if we're talking about water discharge, okay, we need to worry about the cross-sectional area of the free surface. Okay, so now if you recall from our lecture notes, okay, when we have water or fluid discharging or entering into a volume, okay, we have to understand that this principle holds. The volume is nothing but Qi dt minus Qo dt. Qi will be the amount of water that's will be the flow rate that's entering this volume, and Qo will be the water, the fluid that's exiting or leaving this volume. Okay. Now in this case, all right, since we're talking about part A, there's no inflow. Water, all right, is let me rephrase it. We only have water leaving the ship log. There's no water entering the ship log. Okay, so in that case, all right, Qi surely must be equal to 0. So if Qi equals to 0, that means the change in volume, dV, let's just call it, all right, surely if this goes to 0, surely must be equals to minus Q naught dt. Okay, now, We shouldn't be using Q naught here because it will not be compatible with this Q equation. So let's change this Q naught to Q. So that means we can re-express the volume as equals to minus Q dt. This Q surely must be equals to this Q, isn't it? If you think about it. Okay. Now, what's dV? Okay, if you recall from a lecture notes, dV, all right, is the change in volume over dt. And from this schematic, we know that surely must be equals to AS, all right, the free surface area, all right, multiplied by dz, the change in height. So the cross-sectional area of the free surface multiplied by a tiny change in height. All right, that's what dz is. Okay, surely AS dz must be equals to this, but with a negative sign in front, because in part A, we're talking about water leaving the ship lock. Okay, so that means you can set AS dz equals to minus CdA into square root of 2gz dt. Okay, now shuffle the terms around, because for part A, we want to get an expression for t. So surely you have to shuffle the terms such that you have dt on the left-hand side and all the other terms on the right-hand side. Okay, and just nice, you have a z term here. Right, all these things are constant because think about it, AS has got to be a constant because it's a rectangular ship lock. It's not a conical ship lock, thankfully. So since AS is a constant, CD discharge coefficient is a constant, cross-sectional area of the conduit is a constant, square root of 2g is a constant. So take all these constants out from the differential equation. Oh, sorry, from the integral equation. Put them all out. All right, such that at the end of the day, you just have to integrate. All right, 1 over square root z with respect to dz. Okay, with the limits of integration, all right, the upper limit will be z2, the lower limit will be z1. Okay, so I'm quite sure you guys know how to integrate 1 over square root of z. Once you integrate it, plug in the limits of integration, lo and behold, you guys will get the expression that the question is asking you guys to derive. Okay, so that's all. All right, I suppose things help in this case because you know what? This ship lock has got vertical walls. Okay, such that AS is a constant. When AS is constant, it actually makes the things a lot simpler because you don't have to come up with another expression for AS in terms of Z. If that will make the integration a little bit more challenging. Okay, now as for part B, okay, all right, we're looking at a situation whereby the ship lock is being filled instead of being drained. So after pumping out to the reservoir, after they repair the ship, now they want to get the ship out of the ship lock. What do? Well, surely I have to fill up the ship lock with the water again. So in this case, these are the information we're given. All right. The length of the conduit, 100 meters. The length of the ship lock is 100 meters. The width of the ship lock is 30 meters. The discharge coefficient has a value of 0.5. Okay. And delta Z, all right, is 12 meters. Okay. That's what we're told. And we're talking about a time span of 600 seconds because we're talking about 10 minutes. Okay. Okay, let me just refresh my memory what I supposed to find. So basically, how large must the conduit be if the lock is to be filled in 10 minutes? Okay, so the 600 seconds comes from this time requirement. Okay, so we need to find out just how big this conduit is, the cross-sectional area. If let's say, all right, we're supposed to satisfy all these operating conditions and the time, of course. Okay, so now what that means is we can take the formula or the expression that we managed to derive in part A and use it here if you think about it. Because an expression for time t, all right, based on 2 different heights, and we do know the height differences if you think about it. So take all this stuff and simply substitute into the expression that we have in part A. Okay, all right, making sure that you have a negative sign in front because now it's filling. Okay, the sign will be different. And you guys can actually work out what's A. Okay, so I skip the workings, but you guys surely can do the working for yourself. It's just a matter of simple substitution. Okay, please be careful when you punch the numbers into your calculator. That actually sometimes trips some students. Okay, everything is correct except when keying the numbers in the calculators. Okay, so in fact, that's all to part B of question 1. Okay, all right, so it's very interesting. Part A, they ask you to derive the expression. Part B, they're asking you to use the expression. All right, just to see it for yourself. And the cross-sectional area of a conduit is 15.6 meters. That's actually a very big conduit. If you think about it, it's something like 3 meters by 5 meters, you know. But again, right, you're talking about a ship lock that measures 100 meters in length and 30 meters in width. Surely, all right. And you talk about height difference of 12 meters. So naturally speaking, the cross-section of the area of the conduit has got to be large, all right, for this amount of water, for the ship block to be filled within 10 minutes. We're talking about huge flow rate, all right? Okay. Okay, with that, let's move on to question 2. Question 2 is pretty similar to question 1, with the exception that now we don't have vertical wall. We have like a conical wall, all right? If you think about it, it's like a funnel shape. So things will be a little bit trickier. However, all right, do recall that we actually have an example that closely resembles this in our lecture notes. So you can always follow the procedures, okay, of the example that we cover in the lecture notes, okay? But let's run through the question. We have a cone-shaped tank shown in this figure. All right, we're told that it has a 0.2 meter square circular orifice at the bottom. So that's the orifice. That's where the water gets drained out, okay? We're told that this orifice has got a discharge coefficient of CD equals to 0.6. Okay, now given that D1 is 12 meters, what's D1? D1 is over here. That's the free surface at the original height. D2 is 5.6 meter. D2 is here at the final height. Z0 is 10.4 meters. What's Z0? Z0 is the difference between this. Basically, Z0 will be the height by which the water level has fallen. Yeah. And that the water level outside of the tank is constant at 0.2. Where's 0.2? Over here. All right. Determine the time for the water level in the tank to drop from 0.1 to 0.2. So it's very similar, isn't it, to question 1? All right. Chances are we have to come up with some equations. Okay. Now assume that the tank diameter is a function of y and it's expressed as ky, where k is a constant. All right. How about y? Y is actually a function of the height z plus h2. The h2 is over here. Okay, and z in this case will be the variable distance between the two water surfaces. Okay, so again, let's list now what we're able to get from the question. We know that the orifice area A is 0.2 meters squared. Okay, all right, because you can treat the cross-sectional area of the orifice sort of like similar in concept as a cross-sectional of a pipe that's actually deep, right, channeling the water away, isn't it? Discharge coefficient CD is 0.6, D1 is 12 meters, D2 is 5.6 meters, Z0 is 10.4 meters. D is a function of y and can be expressed as ky. Y is equals to Z plus H2. Take note, there's no inflow, there's only outflow. So once again, all right, we know that Qi is actually equal to 0, but that's not the case for Qo. So similarly, let's start off with the basic premise, all right, that governs this such a flow. The change in volume, the volume, all right, once again is equals to the free surface area, AS, multiplied by dz, all right? And this is nothing but, at the end of the day, once you cancel out Qi dt, you're going to get minus Qo dt, okay? And if you recall from the first question, the flow rate through the orifice, all right, has got this formula, Q equals to CD, A into square root of 2GZ. So this is a general expression for flow, all right, through a pipe or through an orifice. Basically anything that gets discharged from a container or a reservoir. Okay, so once again, since we are working with Q, change this Q not to Q, and we have AS dz equals to minus Q dt and equals to minus CdA square root of 2GZ dt. Up to here, all the steps are basically the same as the first question. In fact, the next step is the same as the first question as well. So shuffle the terms around until you get an expression for dt. So dt on the left-hand side, all the other terms to the right-hand side. Okay, now this is where things start to get a bit tricky because you know what? We're no longer dealing with a constant AS. AS in this case is a function of the diameter. Okay, so it depends on the height as well, isn't it? If let's say at this height, all right, at 0.2, surely the diameter is quite a bit smaller, all right, as compared to the diameter at height 1. So, all right, things will be a little bit trickier, but not too bad. Okay, now if we redefine as pi d squared divided by 4, okay, why pi d squared divided by 4? Because it's a funnel, it's a circular funnel. Okay, so the cross-sectional area of the free surface surely must be a funnel. Sorry, must be a circle. All right, that's why pi d squared over 4. So if we take this pi d squared over 4, plug it into here, this is what we get. Shuffle the terms around, okay, just like what we did previously. Take out the constants and so on and so forth out. All right, but at the end of the day, all right, we know that d over here, the diameter, is actually a function of z. All right, we cannot treat d as a constant. So in fact, we have to re-express d as a function of z. Thankfully, the question actually gave us enough information to do just that. Because why? The question told us that the diameter d, okay, all right, is a function of ky. So d squared will be k squared y squared. Hang on, what's y? Y is actually equals to z plus h2, isn't it? So you replace y with z plus h2, and you're going to get d squared equals to k squared into z plus h2 squared. All right, k is actually a constant. So that means during the integration, we can take it out. All right, and we have a z term here, the square out. So what I'm trying to say is, all right, if you substitute d squared equals to this term, plug it back into here, all right, you'll be able to isolate all the constant stuff, all right, and separate it from the z terms. Okay, take the constant stuff out of the integration, or expand the terms here, right, as such, and I'm quite sure, all right, you know how to integrate these three z terms. Okay, all right, okay, and basically, all right, z naught here will be the height difference. Okay, 10.4 meters. Okay, so basically, you substitute all this, put in the integration, you can work out the time to be about 605 seconds. So like I said, what's the difference between question 2 and question 1? All right, the biggest difference is, all right, the diameter here actually varies with the height, whereas for question 1, all right, the free surface area, all right, it does not change. All right, it's constant, doesn't matter what's the water elevation. So the integration here, the integration process here will be a little bit, I won't call it daunting, will be a bit more tedious. Okay, but eventually you have all the information that you need. Okay, so you guys can work out the details, all right, and hopefully you'll be able to get the answer. All right. Now for question 3, begin to move off from this water discharging type of problem. Question 3 is actually a reservoir and pipe flow. Okay, so now we have got a 1,000 meter long, 250 mm diameter pipe with a flush entrance and a friction factor F equals to 0.026 that delivers water from a higher reservoir to a lower one via a submerged discharge. That means we have got a higher reservoir and a lower reservoir. Okay, and they're connected by a pipe. Okay, and this pipe is actually submerged below land. Yeah. Okay. Well, so that's the flow scenario. The question also tells us that we need to treat, also tells us that the minor loss, where k equals to 1, may be assumed. Okay, the minor loss probably comes from the entrance, if you think about it. Okay. Now, the difference between the two water surface elevations is 75 meters. So that means the free surface water height difference, okay, is 75 meters. That's quite a fair bit. Now, after a valve near the downstream end is suddenly open, all right, determine a few things. Firstly, what's the steady state flow velocity in the pipe? Okay, once the valve is open, after a certain time, it's going to reach a steady state velocity. What is that velocity? Okay. Part B, find out the time you'll take after the valve is open for the flow velocity to reach 1/3 that of the steady state velocity. That means now I'm not interested in finding out how much time you're going to take to reach steady state, but actually I want you to find out the time for it to reach 1/3 of the steady state velocity. Okay. For part C, it's pretty much the same thing. As said in this case, all right, we're asked to find the time to reach, all right, 2/3 of the steady state velocity. Okay, I think again this is something that's quite similar to one of the examples in the lecture notes. I don't think you guys should have too much trouble. Okay, but nevertheless, let's quickly run through it. Again, let's know what we have. The length of the pipe is 1,000 meters. The diameter of the pipe is 0.25 meters. The friction factor is 0.026. Okay, that's for the pipeline. Minor loss is 1.0. Delta Z is 75 meters. Now, schematically speaking, this is what we have. A higher reservoir, a lower reservoir. And the difference in the water surface elevation is 75 meters. And we have got a valve that's initially closed, but then, all right, it will be open sudden, all right, and water will start flowing. All right, so basically, water within the pipeline will accelerate from rest. Okay, and part A wants us to find out what's the steady state velocity that this water will reach eventually. Okay. So if you think about it, that means we have to use the energy balance equation. Okay. again, for these expressions, you guys can find out from your lecture material, okay? But for part A, we're talking about steady state flow velocity. So we have to consider, all right, the steady state energy equation, okay? For the steady state energy equation, all right, you guys can use this formula directly, okay? All right, because of this particular flow setup, okay? But I'll advise, what I'm going to advise is always start out with the full Bernoulli's equation, okay? Because that will let you basically account for all the various types of pipeline that you guys going to encounter out there, not just for this higher reservoir, lower reservoir connected by a pipe. Okay, so over here, all right, I did not use the full Bernoulli's equation, but you guys should start out with the full Bernoulli's energy balance equation as a first instance, all right, and basically simplify the terms before you get this. Okay, just to make sure that, all right, you guys are able to account for different types of scenarios. Okay, all right. So anyway, so equation 1 here was obtained after we simplify the unsteady state energy balance equation. Okay, such that at the end of the day, I've got the difference in the Z elevation, or in this case will be H will be set equal to 75. Over here, we have got the flow losses and the minor losses. Okay, and over here we have the unsteady state term. Now for part A, we want to find out the steady state velocity. So that means that this unsteady state term, all right, will have to be assumed to be 0 for our steady state flows. If we assume this to be 0, this equation becomes this expression. And V here, the velocity here, we can write it as Vs, as the steady state velocity, just like what we encountered in the example in one of the lecture slides. Okay, we know that H is 75. We know that the minor losses is 1. We know what's our friction factor is 0.026. The length of the pipe is 1,000. The diameter of the pipe is 0.25. Vs is something that we need to find. G is gravitational acceleration. So at the end of the day, we only have one unknown, that's Vs. Okay, so you guys can eventually, all right, work out that Vs is about 3.74 meters per second. Okay, now let's move on to part B. Okay, whereby we're not asked to find the steady state velocity, we're asked to find the time that we need to take, all right, when the velocity actually reaches 1/3 that of the steady state velocity. Okay, so if that's the case, all right, we have to consider the unsteady state energy balance equation. So this term, all right, cannot be declared to be 0. Okay, all right. So now we can further simplify this. This is an extra step. There's no need for you to do this step, but this is just an extra step. All right, we can further simplify these two equations, equation 3 and 4, if we were to combine, well, all the loss coefficients as K bar. Okay, so equation 3 will become this equation. That means H equals to K bar. All right, V squared divided by 2G plus L over G dV by dt. And equation 4 will be nothing but just H equals to K bar, Vs squared divided by 2G. Okay, remember it's Vs squared here because this comes from the steady state flow energy expression. Okay, so now since these two H are the same, that means I can equate them, or I can substitute equation 6 into equation 5. It's the same thing. All right, and I can start to simplify stuff. All right, after simplifying stuff, I can rearrange the terms here such that I get dt on the left-hand side and all the other terms on the right-hand side. And if we integrate them like the way that we did, I showed you guys in the lecture slides, you're going to get this. You're going to get T equals to L over K bar Vs natural log of Vs plus V bar by Vs minus V. Okay, all right. So this is something that, yeah, all right, that will allows us to find the time, okay, for whatever fraction of the steady state velocity that we want. In this case, it's 1/3, isn't it? So since we want to find out the time t required when v is actually to 1, is like when the velocity in the pipe is actually 1/3 of the steady state velocity, that means 1/3 Vs. Okay, you can substitute this into here. All right, and you realize that Vs will be cancelled. Okay, and you can take natural log quite easily. Surely you know what's Vs, surely you can calculate what's K bar, and surely you know what's L. So plug in all these, all right, T can be worked out to be 1.76 seconds. Now, part C is pretty much the same thing, except that we want to find out the time required for the velocity in the pipe to reach 2/3 that of the steady state velocity. That means V equals to 2/3 Vf. And you realize the T will become 4.09 seconds. So if it's so what's interesting is that for the velocity to reach 1/3 that of the steady state velocity, the time taken will be 1.76 seconds. For it to reach 2/3 of the steady state velocity, time t will be 4.09 seconds. It's not a doubling. Okay, basically this question's purpose is to show you that the time doesn't double just because the velocity double. Okay, because if you take 1.76 multiplied by 2, surely, all right, you're going to get a time that is smaller than 4.09 seconds. Okay, so it's non-linear. Okay, the increment in the velocity, all right, it's not linear. Okay, I think that's the biggest takeaway for this question. Right? Okay, as for question 4, okay, question 4 is a very straightforward question. It deals with water hammer. Okay, now we reference the figure 2 below. I know there are a lot of stuff here, but what's important to note from question 4 is that we have a reservoir and a pipeline, and there's a valve that is shut off abruptly. Okay. Now, so we reference to this figure, we know that water is flowing through this 300 meters pipe, okay, initially at 0.8 meters per second, all right, with the valve open. Now, if the pressure waves are known to travel along it at 1,000 meters per second, determine the maximum water hammer pressure experienced at the valve location if A, the valve is completely closed instantaneously, all right, and basically stop the flow. And B, all right, calculate the maximum water hammer pressure at the valve if, let's say, the valve is actually partially closed instantaneously. All right, so it's a rapid closure, but partially closed. Okay, therefore reducing the final flow velocity to 0.2 meters per second. So this is basically the same as the example that we have seen in the lecture slide. Okay, but nevertheless, let's run through this. So the pipe length, 300 meters, the initial velocity, 0.8 meters per second, Cp or C, all right, the velocity of the pressure wave is 1,000 meters per second. Okay, so essentially this is what we have. Okay, don't worry about this. Okay, don't worry about this. So we have a reservoir and we have a valve. Okay, so now based on the given information, if you think about it, let's just double check it's always good to just work out the reflection time. All right, so that we know. All right, I think in this question, there's no slow closure, so I think we're safe. So it's fine even if you don't calculate it because they are both closed instantaneously. But I always thought that it's a good idea to find out, at least have a feel of how fast, all right, the pressure wave is traveling upstream and coming down again. Okay, in this case, the reflection time is 0.6 seconds, which is quite fast actually. All right, for 1,000 meter pipeline. All right, is it 1,000 meter? No, sorry, 300 meter pipeline. Okay. Okay, now to answer part A, all right, it's an instantaneous, it's a rapid valve closure, all right, with a 0 final velocity. So to calculate the pressure, the water hammer pressure, pH, all right, we just simply have to take the density of the water, multiply by the pressure wave velocity, and then minus off the difference in the velocity. That means initial velocity minus final velocity. But since final velocity is 0, that means we just have to multiply by the initial velocity. Density of water, 1,000 kg per meter cube. I'm quite sure it's something that you guys know how to assume. The pressure wave velocity is 1,000 meters per second. It's given by the question. Initial velocity is 0.8. I'm sure you guys can work out is 100 kilopascal. So that's the water hammer pressure. Okay, once you shut off the valve instantaneously and fully. For part 2, right, we're presented with a scenario whereby the valve is partially closed. Okay, but instantaneously. So thankfully, all right, it's sort of like make things easier because we know that we can still make use of this original equation, except that we have a non-zero flow velocity and a non-zero final flow velocity. So V final is actually 0.2 meters per second as opposed to 0 over here. Okay, but since we're using the same formula, I believe that chucking in the relevant values will not be that difficult if you think about it. So we do have an extra minus 0.2 here. And I'm quite sure you guys can work out that the water hammer pressure is actually quite a fair bit lower as compared to part A. Because you think about it, it's logical, isn't it? The valve in part B, the valve, even though it's closed rapidly, is not entirely closed. water is still flowing through the valve. Okay, and if you think about it, if water is still flowing through the valve, that means that the pressure buildup will not be that much as compared to a valve that is fully shut. Right? In engineering, I suppose that makes a lot of sense, right? Based on the engineering acumen. Okay, but still, it's not that low. It's still 600 kilopascal. All right, it's still 600 kilopascal. Right? And that will be for question 4, actually. All right. Okay. Now let's move on to question 5. Question 5, okay, we'll move on to surge control. Okay, we'll move on to surge control. As you can see, I try to have at least one question from every part of the unsteady flow chapter. So for question 5, we've got 4 meter cube per second worth of water, and we're told that this water is being delivered to a power plant by a 850 meters long, 900 mm diameter circular pipe with flush inlet and friction factor F equals to 0.018. So you can see, right, some of these familiar terms keep cropping up. Diameter of the pipe, length of the pipe, friction factor, and flow rate sometimes. Okay. Now, we're told that this pipe flow is protected from water hammer effects by a surge tank that's located at the downstream end just before the control valve. Just before. Okay. All right. And no distance between the surge tank and the control valve is given. So that means that we can assume that the valve and the surge tank locations are actually at the same place. Okay. All right. Now, without using trial and error, obtain a safe preliminary estimate, okay, of the smallest surge tank diameter that will be required to prevent surges from exceeding 12 meters above the reservoir water surface elevation. So in this case, we're not asked to find the maximum water surge height and things like that. Given the maximum surge height, actually, right? And after that, try to estimate the diameter. So it's opposite to what we have experienced in the example in the lecture notes, whereby the diameter was given and we are asked to estimate Z max. Okay, but in this case, Z max given and we're asked to estimate diameter. Okay, it's the other way around. Now, in solving this problem, all right, we are to neglect all velocity heads and minor losses, as well as fluid friction and inertial losses within the surge tank. Okay, so they're actually friction flow, friction factors associated with the surge tank as well. But we assume that, right, they're negligible, all right, just to simplify matters. Again, list down what we have. We have a pipe length of 850 meters. The diameter of the pipe is 0.5 meters, sorry, 0.9 meters. Friction factor 0.018, that's F, and the flow rate is 4 meter cube per second before the valve is closed. Okay, and this is a scenario that we have. Got a reservoir here. All right, we've got a valve here and the surge tanks here. We assume that they are more or less at the same location, so there's no need to do anything to the L. All right, we assume the L from the reservoir to the surge tank is the same as the L from the reservoir to the valve. Okay. Now, this is the requirement that we're facing. Zmax must be less than or equals to 12 meters. Okay. Now, the first estimate, once again, all right, you can make use of this. Okay. All right. Because this 12 meters is the max. So that means KAS divided by LA times Zmax must be less than 1 or equals to 1 maximum. Okay. So now, okay, that means we can use this expression to find out, all right, the diameter of the surge tank, okay? And basically that depends on us finding the value of AS, okay? So that means that at the end of the day, okay, since we know what's the Zmax, the maximum Zmax, which is 12 meters, we just have to work out the values for cap K, L, and A and plug it in and see what kind of a diameter we are able to get out from AS, okay? So now cap K, all right, based on the formula or based on lecture notes, okay, is nothing but the summation of, all right, the velocity head, the friction head, and minor losses, basically the coefficient of all these losses, okay? But then again, this question told us that all these are assumed, the minor losses and the velocity head are assumed to be 0. So that means you only have to worry about one particular coefficient, and that is F times L over D. That's the pipe flow friction, okay? And we can work out our K in this case, right? Because it's just FL divided by D. We know what's RF, we know what's RL, we know what's RD, and K can be worked out to be 70. Fantastic, because this 70 can be plugged directly into here, okay? And we know what's L L is given as how long? 850 meters. Okay. All right. And I'm quite sure we know how to find out what's the area of the pipe because we know the diameter of the pipe. Okay. All right. So let the diameter of the search tank be D. Okay. And after plugging all these, we can construct this expression. All right. And after you work things out, right, D, the maximum value of D, I set it to equals because I want to find out the maximum value of D. The maximum diameter of the search tank can be worked out rather easily based on this first estimate kind of expression. D should not be greater than 1.837 meters. Okay. If, all right, if you don't want Zmax, sorry, if you don't want Zmax to exceed, all right, 12 meters. Sorry, it's actually the other way around. Diameter should be at least 1.837 meters, okay? If you don't want Zmax, okay, to exceed 12 meters, okay? Because the larger the diameter, all right, the lower the height is going to be for Zmax, okay? All right. So as you can see, all right, even though the theory behind all this, right, may seems to be quite complicated, all right, everything boils down to you guys, okay, knowing how to use the steady state and the unsteady state Bernoulli's equation or the energy balance equation. Once you know how to simplify, okay, or construct the Bernoulli's equation or the energy balance equation according to the specific pipeline, okay, the rest is just a matter of simplifying it, all right, putting in the relevant values, okay, understanding the scenario, understanding what you need to find, and find the unknown, all right, in a systematic manner. Okay, there's nothing hard per se, all right, for unsteady flows. Okay, if I were to say turbo machineries will be more difficult than unsteady flows. Unsteady flows, pretty much everything hinges upon, right, the implementation or the applications of the steady state or unsteady state energy balance equation, to be honest. Right? Doesn't matter if we're talking about surge control, doesn't matter if we're talking about water handling effects or just general unsteady flows, right? Okay, from one reservoir to another reservoir. Okay, all right. So that will conclude this particular tutorial. Okay, so if you have trouble understanding where some of the concepts are, all right, feel free to replay the videos. Note that for some of the questions, I did not show the detailed workings because I think it's something that you guys should know what to do already. Okay, I just merely show you the general steps. Okay, the punching of numbers on calculators. All right, I'm quite sure you guys have more than enough skills to handle it. Okay, all right. So I think this will conclude my tutorial. And with regards to the request to cover, maybe have a mini review of some of the major concepts. I think let me record a video. Okay, it may not be immediate, but probably it will be out, let's say, after the 30. Will that be okay? All right. I hope that will be okay, yeah? All right, because right now I'm still teaching. Tomorrow is CA. Can you imagine how many CA answer scripts I'm going to mark? I don't look forward to it. But I'll tell you what, okay, please revise for your CA tomorrow, okay? I still try my best to answer any questions that you guys may post to me through email or text or Teams, but sometimes it'll take a while because a lot of students are asking me questions, okay, and it takes time, and I still have meetings and stuff to go to. I need to go to the lab and so on and so forth. So it may take some time for me to get back to you. If you're lucky, I can get back to you, and I happen to be right at the computer, I can probably get back to you very, very fast. If I say if I'm in the lab doing some setting up for some experiments, then maybe it'll take a while. Okay, so it really boils down to the luck of the draw. Okay, all right, people. All right, thanks very much. I wish you all the best for your CA tomorrow, and I'll see you guys in NT tomorrow. Please double check your LT, all right, and to know where you're going to go, all right, because at the end of the day, all right, the seating arrangements are fixed, okay, to ensure that we don't exceed 50 people. Don't go to an LT where you're not supposed to go, because in case of anything, the contract will do the contact tracing based on the LT allocation seating, at LT allocation list. Okay, so if you for some reason decide to switch to another LT, okay, without letting me know, without a good reason, okay, I'm not going to mark it. Okay, I'm not going to mark a CA. All right, because why? I mean, I think it's very simple to follow this very simple rules. Just stick to the LT. All right, that's allocated to you. Please see that we have to make sure that everyone is safe, or at least, right, things can be done if, let's say, all right, something happens. Okay, don't jump around. All right, okay, it's 12:32. You guys must be famished. I'll just let you guys go. Have a nice day, and I'll see you guys tomorrow. Okay, bye. All right. Thank you very much. Bye.